Hey, we're starting our research jam number 20. So hard to imagine that we're hitting 20. And it's also almost exactly to the day, 3 years from our first one. Yeah, it was March 29th or something. So thank you for joining, whether you're here for the first time or the 20th time, welcome. We are a space where people just sign up to present their work and are willing to share, be recorded and shared on YouTube and into our community for free and to receive maybe opportunities, mentorship, and other kind of assistance. But it's a space for open science. And we welcome two speakers today, Razvan and Jayu. Razvan, you can get started if you want.
Great. So, hey everyone, my name is Razvan. I'm an undergrad at U Montreal. So, lower your expectations, please. Yeah, I've been working on something for, let me share. Yeah, so I've been working on this thing for like 2 months now in between classes. The formal title is Neural Network Loss Landscapes Are Stochastic Narrowing Valleys, or Why the Hell Do Negative Eigenvalues Persist in Hessian? So the main idea here is, at the beginning was to basically try to understand, try to get a mental picture of loss landscapes in general, right? So like when I began learning deep learning, I sort of got told, well, because these networks are like 30 million dimensional, and the loss landscape is non-convex, and so like don't even try to imagine it because it's like super impossible, and any intuitions you can build won't like extrapolate to 30 million dimensions, so don't even try. So my goal today is going to be to kind of provide a simple two-dimensional kind of mental model of a loss landscape that recaptures a bunch of the characteristics that you've seen in neural networks, right? Okay, so here's my email. Can you guys see my cursor? Yeah, okay, so here's my email. Email me any papers. If you see, I'm gonna be probably building a paper out of this, depending on like how lit review turns out. Yeah, email me if you want to chat. Okay, so before I can go into what the hell I did here, I have to kind of go into a bit of linear algebra review, just to kind of get everyone up to speed. So any n-dimensional function can be approximated up to second order by this guy, where H is a symmetric matrix that we call the Hessian. You can diagonalize H in this way, where here Q is orthogonal, and big lambda is going to be just a diagonal matrix made up of the positive eigenvalues or negative eigenvalues. And this set here is called the spectrum of H. Right. So today we're going to be concerned with how the spectrum of H changes throughout training. So the fundamental quantity here is the spectrum of the Hessian, and that's what we're going to be concerned with today. On the right here, I have a simple two-dimensional function that's like a saddle shaped with a positive eigenvalue here and a negative eigenvalue here. And you can see like straight away here, if you try to do gradient descent on this 2D function, in some way, the negative eigenvalue direction here is the easiest to optimize. Right? Like any initial kind of, as long as you're not literally at zero exactly at the beginning, any initial displacement will be magnified exponentially in the negative eigenvalue direction. And these ones are much easier to optimize than the positive ones, right? So yeah. Okay, now that everyone is, yeah.
So just to this maybe for myself, but out loud for other people as well. So if we had a one-dimensional quadratic, that might be x squared looking like this. If we had a 2 or 3-dimensional quadratic, that might be x squared plus y squared plus z squared. So the Hessian would be, I guess, 1, 1, 1. The spectrum, I guess, would be 1, 1, 1. Is this so far so good?
Yeah.
Some numbers get bigger and things get steeper or smaller and dimensions get flatter or negative, and then eventually we have this other curvature, this saddle point, right?
Exactly. Yeah,
okay.
That's it. And with pure quadratics, you can basically also always like, so the basic form of a quadratic is just x squared plus y squared plus z squared, and you can like turn it depending on your choice of q here. You can sort of rotate it in n-dimensional space however you want. So like you can, if you're quadratic, you can always rotate it such that it's going to be like a sum of square terms without cross terms.
Yep.
Yeah, and if your eigenvalues are larger, this direction here is steeper, and yeah, that's the basic form of like a. In general, it's going to be like a saddle shaped or a bowl shaped.
Okay. So going back to your title slide, what were you surprised about? Why do we still have positive eigenvalues or negative eigenvalues?
Negative ones. So the whole point is, for later, but like when you Hessian for a real network, you do find these saddle shaped functions all the way to the end. right? So like the surprising thing here is like these negative directions are supposed to be really, really easy. Like they're supposed to be the easiest ones out of all of them to optimize. Like why are we still have them even at the end? So that's the fundamental kind of surprising thing here. But okay, so this is the linear algebra review here. Let's train a network, right? So let's do a simple kind of very, very small network on Scipher 10. So here I have only it's a ResNet with only 26,000 parameters, mostly because you have to compute the Hessian weights, and 26,000 by 26,000 is going to come up like 4 gigabytes. Just from the outer like space constraints, you just can't compute the Hessian for super big networks. So okay, so we trained this network with like SGD, and we decrease the learning rates every 10,000 iterations, which is like every 500 epochs. And you get kind of 4 weird things that happen when training a network. The first weird thing is you get this loss decrease every learning rate decrease, right? So from a like if you're thinking of optimization as a mountain descent type of thing, it's sort of weird that every time you decrease the step size, you kind of go down in loss, right? You're like this descent mountain, and you decrease your step size, and suddenly you go down a crater. Like there's something has to be explained in that phenomenon, kind of. Second weird thing is if you increase the batch size, you get the same effect as learning rate decreases. And again, that's sort of weird if you're picturing this as like a smooth mountain descent. Third one is as you go through training, your largest eigenvalue will increase. So your sort of spectrum will this is called the edge of stability phenomenon. All right, so like your largest eigenvalue will basically increase until it's unstable, right? So that's sort of a weird thing. And the last thing is you get negative eigenvalues all the way up till the end. You never end up optimizing those like downward sloping directions. So the goal is to kind of get an overall picture that makes sense of these 4 things. And so
Can
what I'm claiming.
Can you tell us what you're showing in this plot? What are the 2 lines?
Oh yeah, so the blue line is the loss of the network, and the red line is the maximum eigenvalue through training.
All right, thanks.
Thanks. Just as an aside, the network gets 80% validation set at the end. So it's not like standard, like good or anything, but it's not a toy model. Like you don't get like so it's more than a toy model, but not as good as state of the art, basically. So the goal today is going to be to like explain these 4 things in a coherent way. And what I'm claiming is that you can build like 2-dimensional models that have all these 4 things in them, and you don't need to like imagine 30 million dimensions. Okay, so we've trained this network, and we like decrease the learning rate every 50 epochs. Let's compute the Hessian at a bunch of points, and let's plot its spectrum, right? So these plots are a bit weird. I'm plotting the rank of the eigenvalue versus its like value here for a bunch of points through training. So each line corresponds to a point in training, right? The red line is the initial like iteration 0, and then all these lines correspond to iteration 10,000, 20,000, up until the end 50,000. And this is the kind of log plot of the rank versus eigenvalue for the positive eigenvalues, and this is for the negative eigenvalues. And there's a bunch of things to say here. For the positive values, you basically just get an overall translation upwards or downwards. Like the shape of the spectrum doesn't really change for the positive values, right? You as you go training, it kind of all values go upwards or downwards together, but you don't really get like a shape difference, right? So that's number 1. And then so the upward training eigenvalues is the edge of stability. It's the thing we saw in the last plot where the largest eigenvalue kind of increases through training. And on the negative side, so okay, as you train, all the negative eigenvalues do decrease, right? But they never go to 0 really. Like even at the very end of training, which is this green line here, you get 2,000 directions almost out of 26,000. So like 10% of the directions are downward sloping, right? Even after like 500 epochs, even after having decreased the learning rate by a whole bunch, you still get these like 2,000 directions that are supposed to be super easy to optimize. Yeah, so something weird is going on in this whole picture, right, that we want to figure out. And to figure this out, let's do a bunch of line searches. Right, so basically, so you have your network, fix it at iteration 10,000. Right, so you train for 50 epochs, find a positive eigenvector, and then do a line search in that way for every one of your mini batches. And this is what I'm plotting on the left here. So each line here is a line search for a particular mini batch in one direction. And you can see that basically all mini batches are just like quadratics translated upward, or like up or down and left or right. But all of them have the same shape. They're all basically quadratic. And all the blue points here are the minimum of each curve. So
what's the x-axis here?
this is just a scale. It's like, so at the middle here is the network without any like line search, and it's just like an alpha parameter going that way or like coming down the line search.
But
it's like
does 20 correspond to like the current solution, the current parameter?
Yeah, so the middle point corresponds to the current parameter, and as you go right and left, it's like alpha 1 and alpha minus 1. It's like the scaling here is just to show interesting behavior. Like if you choose the scaling too small, you're going to get like straight lines, and if you choose it too large, you're going to get like weird stuff. So this is just like arbitrary scaling to show interesting behavior. Yeah. So these are the positive values. All this is not cherry picked. Like all positive eigenvalue directions behave like this, and all negative directions behave like this. It's just like scaled by one factor or another. Okay, so the positive directions behave sort of like you'd expect. All mini batches are quadratic. The shape doesn't change necessarily. It's just like this. It's the same eigenvalue for all mini batches. It only changes in the minimum location. But the negative eigenvalue directions are kind of weird. So for each mini batch, I'm plotting the blue point is the global minimum for that direction. So mini batches disagree about which of the two minima is the correct one. So that's interesting thing number one. And the second interesting thing is the network settles at a point which is a global maximum here. So the midpoint is the point at which the network has settled at a duration 10,000. And when you do a line search in that direction, it turns out to be a global maximum, or like a local maximum here, right? So the network has settled down to a local maximum in that direction, which is a weird thing. Like if you SGD on this one-dimensional function by itself, it's going to take 20 iterations to just find one of the two minimum here. So there's like a weird thing going on here that needs to be explained.
Sorry to ask so many questions. Are all of these different lines, different rainbow, are they different mini batches, or are they different negative eigenvalues?
Different mini batches. So all the eigenvalues behave like this. It's just going to be like stretched out here. So each line here is a different mini batch. So there's like stochasticity in the line going to be important, but all of them are basically the same shape, just translated up or down. And the matter because you're taking gradients, right? So in the actual dynamics, the only thing that matters is going to be the x translation, not the y one.
And what are the colors of the lines?
Colors just to differentiate them. It's just to like pick them out easier. Yeah. There's no like the red or blue one. Apart from like I made the red ones be like I chose them to be smaller, and like the lower ones were red and the higher ones were blue. But there's no other meaning than that.
Okay, so they're all the exact same eigenvector, not the right. Might be worth it to put a vertical line to indicate where the solution is. I know it's in the middle.
Yeah.
Hard to see, hard to tell if it's the global maximum, as you said.
Yeah, sorry. I had made these plots a while ago, and I didn't want to like rerun all the like 15s anyway.
I would just do Keynote's trick to add where I think it is. So have you tried other eigenvectors?
Yeah. Like they literally all behave in one of these two ways. If you have a positive eigenvector, it's like the left one, and if you're a negative one, it's like the right one. So you basically have like two different behaviors here. One, yeah. There's no like third way that a line search can behave really. At least in the small network that I had. Okay, so we have these like weird things that the network does. Let's try to build like toy models that reproduce this, right? And I can think of basically two models that exhibit these behaviors. The first one is one-dimensional, and the second one is two-dimensional. Let's go through the one-dimensional model first. So suppose you're optimizing a quadratic function, just like literally just optimizing x squared. Only every time you kind of sample the function and its gradient, the function is slightly moved left or right. Like it's x minus epsilon, where epsilon is a normal variable with some variance sigma squared. So what's going to happen is, and here I'm plotting, so the blue lines are different kind of samples from the random quadratics, right? So what's going to happen is you start out here, and then when you're here, the gradient of all of them kind of agree. It's going to push you down. And then once you get close to zero, you get a balancing effect. SGD is going to want to like push you down towards zero, and the noise is going to want to like push you away from it, right? So at SGD, with a given learning rate, with a fixed learning rate, you're sort of going to oscillate around 0 with some fixed variance. So here, the red line is kind of the variance of the noise. It's the variance of epsilon here. And the yellow lines and the green lines are the equilibrium distributions that SGD finds with different learning rates. And it's a bit of a pain in the ass, but you can do it. Like the equilibrium distribution is going to be Gaussian with this variance. So here, alpha is the learning rate, lambda is the eigenvalue for that direction, sigma squared is the variance in your noise. And if you know all of these things, you can know that SGD will settle down around 0 with this variance, right? And given this variance, you can compute the expected value of a function, which is going to be this. And so at a given learning rate, you're going to get a finite expected value here. It's not going to be 0. You're not going to get to the minimum. You're going to oscillate around the minimum with some variance. And this variance depends on alpha and on sigma squared. So this kind of captures two of the phenomena that I said were weird at the beginning. In this model, when you decrease the learning rates, your equilibrium level will decrease by the same amount. So when you decrease the learning rate, you'll start oscillating around 0. And so your expected loss is going to be smaller. And if you increase the batch size, your noise will decrease. If you increase the batch size by 10, the variance in your oscillation will also decrease by 10. And so sigma squared will decrease by 10, and your loss will decrease by 10. Right? So this kind of one-dimensional toy model captures the first two weird phenomena here. Now let's go with the 2D toy model here, which is aimed at capturing the last two. So I'm plotting here, this is not a true loss. It's just like I decided on this function and I'm plotting it, right? Which is like a narrowing value type of thing. So you also imagine this function kind of oscillating stochastically left and right and up and down. And so when you do SGD on this function, you can kind of imagine the path is going to start here and it's going to kind of go follow the gradient here and then do like a U-turn towards the minimum. And the idea with this function is to try to capture the edge of stability thing. As you get closer to the minimum, the eigenvalue in the y direction will increase. So the function is much sharper here than it is here. Right? So this is meant to capture that thing. And if you don't have any noise in this function, if you don't consider it like stochastic, you'll just get closer to the minimum and that'll be that. You won't have any weird behavior. The weirdness comes when you think about this as moving up and down and left or right stochastically. So let's figure out what's going on here. On the left plot, I'm plotting like the x gradients of function. So the red regions corresponds to the regions of the function where the x gradient points towards the minimum. So if you descend and you're in the blue region, initially you'll go away from the minimum, which is this point. And if you're in the red region, then you'll go towards the minimum. But now if you have a function and you're at this point, you'll the equilibrium distribution will make you oscillate in y with a given variance, right? And as you oscillate in y with a given variance, you'll sample points both in the red region and in the blue region, right? And the points in the blue region will point you from the minimum, and the ones in the red region will point you towards the minimum. And at equilibrium, those two effects have to cancel out, right? So as you do SGD here, you'll kind of oscillate here, you'll get closer, closer, closer until where the blue region dominates and makes you kind of settle down here, right? So you won't settle down at the minimum. You'll settle down some points away from it.
Say that the red point bring you, if you take an infinitely small step, slightly closer to the minimum. Blue points take you slightly further away. Here you're only showing the sign, whether it's positive or negative. And if you want to evaluate the long-term kind of equilibrium behavior, I suppose you also need to consider like the direction that the blue points take you. Like it's not as simple as just saying you're going to oscillate between positive and negative signs, right?
No, yeah. But the idea is like if you have a large enough learning rate, just the thing to take away here is you won't oscillate exactly at the minimum. You'll oscillate some distance away from it, right? Because if you like close to the minimum, basically none of your oscillations will be in the red region, and all of them will be like the red region. Yeah. This is just like a qualitative. You won't oscillate centered around the minimum. You oscillate a bit away from it.
It'd be interesting to generate this plot, but zoom in closer and closer to the minimum and see, does that red region, does the angle actually kind of decay towards 0? If so, with the point you're making, definitely true, right?
Right. But yeah, but that's okay. The next point is, suppose you're oscillating in this region here, and you stop. You just stop the oscillation, and you take that point and you evaluate this Hessian. And here I'm plotting in this red region are all the points of this landscape where the Hessian has at least one negative eigenvalue, right? So this would be, you're oscillating here, the gradient, you stop, you pick a point, and you look at its Hessian. Here. And then if you're in this red region, your Hessian will have one negative eigenvalue, or at least one, right? So you see that this blue strip here of purely positive eigenvalues is very thin. If you're oscillating with a large enough learning rate, the points at which you stop will probabilistically be have at least one negative eigenvalue. But this negative eigenvalue is kind of spurious. Like, it's not because you can't optimize along this direction. It's because you're at equilibrium. Like, you've descended along this landscape as close to minimum as you can. It's just your noise is making you oscillate here. And so when you stop, you're probably going to land in this red region instead of this blue region here. And so this kind of toy model captures the last two effects. The last two effects where, as you get closer to the minimum, your largest eigenvalue increases. So the sharpness in this direction increases. And also negative eigenvalues persist to the end, basically, because the negative eigenvalues are a sort of phenomena of noise. You're like noisily oscillating down this valley. And when you stop, you find one negative one. All right. Okay, so this is a toy model. Like, this is not an actual real network. But let's try to think of what predictions this toy model can make, even for real networks. Right. So at least a qualitative prediction. And one prediction that I can come up with is, if you optimize, if you have a real network and you find its positive eigenvalues and you optimize along them. Right. So in this scenario, it would be, you're here and you find the positive eigenvalue and you optimize, you do a line search along it and you find the blue region. And then you compute the eigenvectors here. So the negative eigenvectors should at least be smaller or have disappeared. So the prediction is, if you have a real network and you do gradient descent in a subspace which is like really high eigenvalue, the negative eigenvalues should decrease after that. Like, after having found the optimum in the high eigenvalue subspace, your negative eigenvalues should be like less pronounced, basically. See, like, there's like this coupling between the high eigenvalues and the negative eigenvalues that is non-trivial. If you optimize along them, if you optimize along the high eigenvalue, your negative eigenvalues will decrease. And this is, as I was doing this project, this was like an actual real prediction. Like, I didn't know the answer beforehand. I made this toy model and I figured out like that this should happen. And then I did the experiment. And the experiment turns out to bear this out. So here, each curve is, again, the spectrum, as I had a few slides ago. This is the positive spectrum and the negative spectrum. And each curve here is like the model after having been optimized along an increasing number of high eigenvalue directions. So the red curve is like, okay, choose the highest 12 eigenvalue directions, optimize along them, and then compute the spectrum. And then the curve of 500 is find the 500 largest eigenvalue directions, optimize along them, and then compute the spectrum. And when you do this, you see like this like the negative eigenvalues, whereas the positive ones don't really change, apart from the last one. Going back here, if you're like here and you optimize along this direction, you find the blue region. The blue region that doesn't have the highest eigenvalue here is the same as it was here, right? There's no change. Whereas the negative eigenvalue here is very, very large, and the negative eigenvalue here has disappeared. So in this sense, this is for a real network, the same one that I had before. Notice that this is not a trivial effect. Like, if you're really approximated by like a shape, what you should observe is like no change in the spectrum either way. So as you optimize the high eigenvalue directions, you shouldn't change at all, right? So this is kind of showing a coupling between high eigenvalues and negative eigenvalues that is predicted qualitatively by this simple kind of narrowing valley toy model. Okay, but now it would be really nice to have like a plot of the network itself showing like a narrowing valley. But so far, I've only shown like narrowing valleys in toy models, but who knows what the network is really doing. So here I'm plotting a contour plot of the loss landscape for two directions here. The x-axis is the largest eigenvalue, and the y-axis is the value direction, which is kind of non-trivial to find here. I have this like procedure that we won't really include, but like if you do this, you can find a curve. You can have a parametric curve in the lost landscape, which when you do like a contour plot along it with the largest eigenvalue, you'll find this shape here, which is like very close to the toy model I had, only like stretched in a weird way. You see like, so as you go down the network, you get very, very sharp kind of eigenvalue at the very end here. So networks, you really do have subspaces of real networks that are narrowing values. Yep. That's all I have. The conclusion is, think of the lost landscape as a stochastic narrowing valley. And I mean, that at least helps me like in advance how the network will behave. If you learning rates, this predicts the loss like decrease and stuff. Yeah, the only I guess one thing that I haven't been able to figure out is like, should we want to go down the narrowing valley? So when you decrease the learning rate, you kind of have two effects. You have the effects along the high eigenvalue, which will just like bring you to a lower equilibrium level, and you have the effect along the narrowing valley, so you like go down to a lower equilibrium level, and you also go down the valley, right? So I'm not sure which one is generalizing and which one is not generalizing. Like, is going down the valley the price for optimizing the high eigenvalues, or should we want to go down the valley for its own sake, right? That's like, which of these two effects are leading to generalization is kind of the main question that I'm interested in right now. Yeah, that's it. Thank you. Questions, comments?
Great talk. Great project, actually.
Thanks.
I have a quick question. So I'm a little bit fascinated by so your toy model does not have local maxima, yet it still had, like, even within any particular batch, yet it still has the same phenomenon as in or does have local maxima. How do you do that?
Oh, sure. Let me just reshare the screen here. Okay, so when you go here, yeah, suppose you're at this point, right? Or like, yeah, you're here. And this point has a negative eigenvalue because it's in the red region. Now, the negative eigenvalue at this point is gonna be this direction. It's gonna look like the positive eigenvalue is gonna be like this. Sorry, like this, and the negative one is gonna be like this. Right now, suppose you take a line search in the negative direction. You're gonna line search like here. So take this line. This line is gonna have a local maximum at this point. Because you'll go down the minimum, but also in this direction you'll go down. Like the contour curves, the contour lines are curving away from it, which means that this point is at a local maximum in this one-dimensional function.
Got it. Thanks.
Right? Yeah. That's like a weird, yeah. So like being at a local maximum in one line search direction doesn't imply a local maximum in n dimensions. It's like a weird effect.
In interest of time, let's move on to Jay. I think Razvan again.
So for this project, I've been working on it for a few months now, and our goal was to create an autonomous agent that could complete tasks on the website on its own through only using the GUI, just by seeing the screen and, controlling and clicking with the mouse. And the motivation for this is if we could create such an AI that it could generalize to the majority of digital environments without having to rely on API programming. And this could have many beneficial implications to a lot of different technologies, especially, for example, like computer accessibility for the disabled or digital assistants. And we want to use open source large language models for this because they're much cheaper, faster, and also for reasons such as data privacy and customizability. And on the right here, this is just like a quick example of, a type of task we might want, I guess. So like, please bookmark all Twitter posts from this user. And to human, it sounds like a very simple task, but for an AI, it's still quite difficult because there's, a lot of actions that need to be taken, and it also needs to reason about the content of the web page and then choose the correct thing to click at each step. So just a quick background. So web navigation originally started as a reinforcement learning benchmark type, but in recent years, based agents have also been showing potential because a lot of them have seen HTML data in their pre-training, so they're like somewhat capable. Even zero shot, there are still many challenges. For example, with LLM agents, like they usually interact with elements through the page HTML, which is how they understand what's on the screen. And also recently with multimodal LLM agents, these have been quite useful recently as well because they can see the screen, which oftentimes like contains like important information that's not present in just the page HTML. But these have still have many like challenges associated with currently because screens these days are like really high resolution, like usually like 1920p at least. But current vision models, they're limited in their max resolution, so they need to downscale the images, and then you lose lots of detail, especially like with the smaller elements or like icons or text. And also for open source multimodal LLMs, they definitely have like noticeably weaker text-only reasoning ability compared to like some of the better text-only LLMs like Mistral, for example. And the current state of the art at the moment is like agents that use GPT-4V as the multimodal LLM, and they kind of have it in a decision-making loop that like keeps prompting it and asking it for the next action to take. So our idea for this project was kind of to combine an LLM together with a multimodal LLM to sort of try and sidestep the weaknesses of both by having them work together. So this diagram goes over our basic approach. So we have an LLM and vision language model with specialized roles working together. So vision language model, it can take in the screenshot input and then describe like, what's on the screen, what elements are available, and then provide a natural language description to the LLM planner. And this description tends to be like both like more informative in terms of like semantics and also more concise compared to like, like the full page HTML. And then based on the description of observation and like the previous like, episode history, the LLM planner reasons about the current task to decide like what the next action should be. And then it sends a command to the visual language model. We use Cog Agents 18B, which is a very recently released multimodal LLM that was trained like specifically on web page screenshots, and it can interact with the screen by clicking just through like outputting XY coordinates, and then so that's our basic approach. And we also for the vision language model, we implemented a divide and conquer algorithm to split the screen into smaller sections one at a time to make up for the current limitation of like the visual model the max like input size. So this is a good example of what might be a website that would be like too challenging for current multimodal LLMs, like even GPT-4V still struggles on something like this because there's just a lot of information on the screen and a lot of the details are very small. So it still like can miss relevant details or gets distracted by irrelevant information. And like a major thing is it really struggles to click accurately still. And especially if we're using We'd prefer like them to be able to like click the correct like location the first time, because we don't want to like call it over and over again. You try and get it to click the correct spot. So what we do is we just ask the visual language model with the natural language description of the region that we want, and then it provides the bounding boxes on the screen. So here we ask it for the main area of the website, and then it'll crop out the sort of the large section of the screen containing just the, and then we can crop the image and then zoom in just on the products and have it like focus on just that section. And then if we want to, for example, analyze the details of each image, you know, like much more precisely, we can just like give a natural language description of what part of the screen we want to focus on, and then like it'll understand it and then give us bounding boxes, and then we can crop again and zoom in, and then the VLM analyze the image in much greater detail. And another benefit this has is it allows like much more precise clicking. So for example, we can just ask it to click the gift ideas link, and on the full screen, this is quite small, but when it's zoomed in like this, it'll, from our tests, it like is able to click almost like 100% accurately. It's pretty reliable if it's zoomed in. And then this is an example of asking it to give a description of what it sees on the screen. And then again, when it's focused in on one specific type of content at the same time, if we go back, like on the original screen, that sidebar is like kind of taking up a small like area on the edge of the screen. But if we zoom in on just that content, then it's able to provide a much more detailed and accurate description of what it's seeing. And I like read through this whole description, and like I'd say like it's almost perfect. Like there's one very minor error in there, but it's not a major deal. And it not only like mentions all the like relevant information on the screen, but it also, since the visual model was trained on websites specifically, can understand like sort of like what the purpose of these elements are, like recognizes that these are filtering options for an e-commerce site. And then based on this description, the LLM planner can understand really well what's going on and like what options are available on the page. So yeah, we've been working on this project for maybe two months now. And yeah, so currently we have a working decision-making algorithm, like kind of like, you know, our like prompting loop between the LLM and the VLM. And then we're getting close to finishing our first version of the project code. So maybe one week out, I'd guess. And then, but we haven't started any training yet. So the main thing left to do, the largest time chunk, definitely is creating a specialized training data set for the LLM, because with the planning module, Mistral 7B is like, it's reasonably good at the moment, like, as is, especially with a few shot examples. But we think we can definitely like improve it a lot further with specialized training. And then yeah, after that, all that's left is training the LLM and then running final benchmark runs. So we're currently 4 people at the moment on this project, all of us from the ML Collective Discord. And then we think some people who would really enjoy working on this project would be people who enjoy working on like applied projects, like in natural language processing, computer vision, reinforcement learning, or human-computer interaction. And yeah, like before this project, I wasn't that familiar with human CI research, but I've actually incorporated a lot of each research ideas in this. And yeah, the main thing that we would be looking for collaborators for would be making the instruction tuning data set, because it's quite easy to scale with lots of people. And also if anyone's kind of focused on AI safety research, like maybe that would be good as well, because I suppose for the autonomous agent, like maybe that'd be a good thing to think about. And also we're planning to write a paper and submit to NeurIPS, and this is gonna be my first paper. So if anyone has more experience submitting to major AI conferences and would like to sort of like just like take on like an advising role, then that'd be very helpful for us as well. So I think that's it. And I just have the papers that I mentioned. I'd say this is a pretty good overview of the current state of web navigation agent research. So yeah, that's my presentation.
Nice,
Cool.
Jay. Thanks for the presentation. Can I ask, do you think your main contribution here in a paper would be a data set other people can use, modeling ideas, or something else? Evaluations, I guess.
Yeah, I guess our main contribution would be design of the agent algorithm. Sort of instead of like having the model analyze the whole screen at the same time and then choose like what to click next. Like we have our process where we kind of like divide and conquer the screen into smaller sections and then analyze each section at the same time. And also I'm pretty sure we're the first group to implement sort of like a multi-model like LLM combined with the vision language model combined together for the web navigation test. So yeah, that would be the main contribution, I'd say. But also, I suppose the data set, we'd also like release it, and that could potentially be useful as well.
Could be a nice NeurIPS demo too, if you focus more on the tool, the usage of the tool, and how you can showcase the capability and make it a more demo friendly.
I don't know how hard it would be, but releasing a browser plugin too could be really fun. So people could literally install it and try this out on the web. And then if you release that, I think people would build 100 other fun toys and tools using this as a framework.
That's part of the plan as well.
Cool.
I have a couple of questions. One is regarding, so this framework takes a screenshot as an input, right? Or does it take both screenshot and its HTML also?
It only uses screenshot.
Okay. Yeah. So I was just wanted to share you that seems like both screenshot and HTML works better compared to HTML alone or screenshot alone. There was some research going on this direction as well, where they are considering both and they are finding better results. So just wanted to share with you guys whether this could be helpful for you in your research. And the second question is that I have seen a couple of projects with multimodal navigation. I don't know if you have chance to go through them, like Microsoft UFO. Yeah, like they came up with a framework. I think so they're using just screenshot for navigation, not both HTML and that, because they are focusing on not only browser but also the operating system as well, like applications, different parts again. So what do you think of them, and how different do you think this could go on for your research?
Oh yeah, I like that paper. Yeah, definitely. That paper uses GPT-4V, I'm pretty sure, which is much more capable than our open source model. So yeah, basically their approach is like they use less steps, I guess, with the GPT-4V. You can just like feed the whole screenshot to the agent and then decide the next thing to click. But for our project, we use like more steps, divide each problem into more steps to kind of like make the problems more manageable for the smaller like models that we're using.
Got it. So like you added this zoom action also, right? I mean, I need to zoom into this particular area. So you will be having that function where you can particularly zoom in that and take a screenshot, and you will be sending it, right?
We use the agent to decide like which part of the screen to crop so that we don't
Yeah,
kind of like cut off elements or like.
Yeah, I think that will be the USP for your research, because I haven't seen personally where the zoom action. So like basic actions are mouse, keyboard, click, press. These are the basic actions, right, for any multimodal navigation. I think this zoom action is very different that no one else is doing. Yeah, that's great.
Any other questions?
I have a question. How are you choosing the prompt to focus in on a specific part of the screen? And did you use any evals to decide on that prompt, or it was just like, this one works pretty well?
We tested a lot of different prompts, and some of them they work well on certain websites, but some of them not so much. But we found some prompts that are very like general and the model responds well to, like on any screenshot. So we just like just tried a bunch and then found some ones that work really well.
Cool, thanks.
Not a question exactly, but I'll be excited to see any update if you guys want to present an update at the next research jam, in particular how the kind of paper writing process went for NeurIPS. If people want to get in touch to collaborate on this for the paper push, how should they reach you guys?
Yeah, I guess either I'm in the ML Collective Discord is just my name like JU, or my email's first slide, I think.
Do you guys have a group on the Discord? Do you want a chat room? I think it was just people working on this project or interested in. We can create one, either private or public.
That'd be a good idea, I think.
I can follow up.
Yeah, that'd be great.
Hi there, I'm Jonathan. Thanks for having me. I'm going to be sharing a little bit about our open initiative to reconstruct imagery from EEG. Some background context, a few members of our group worked on MindEye2, which was an image reconstruction project from fMRI. The main contribution was by using multi-subject pre-training, we were able to decrease the fine-tuning time 40 times. And this whole field of image reconstruction has been blowing up a lot in the past 2 years as we're seeing the growth of huge data sets and models that are able to understand sort of complex neuro data. Generally for reconstruction, the pipeline is like this. You have an image stimulus and you measure the brain response from that. You take that and you pass it through a deep learning model and you try to reconstruct the original stimulus. So what we're trying to do an end-to-end image reconstruction project from EEG. So this involves gathering our own EEG data set and then pre-processing it, then training our own end-to-end models to go from EEG data to imagery. And the reason we want to have an end-to-end pipeline is because when we have the participant and the headset and the hardware, we can do some experiments that we can only do when we have all of them. So we want to explore domains such as imagined imagery or dream imagery, or exploring how well we can reconstruct in natural environments that are very noisy. So nobody has really done this yet, and that's why it's really exciting to us. We made a big data set and we submitted that to a CVPR workshop just a few days ago. And when it's on archive, feel free to check it out. It explains a little bit of the current dynamics of EEG models and data sets and kind of what's lacking in the field right now. So our general pipeline is inspired by EEG image decode, which was a recent paper that came out. They use imagery, they pass it through an encoder, and they try to train an EEG encoder that learns a similar embedding. And they take that embedding and they try to pass it through Stable Diffusion to guide the diffusion process. So the encoder that we're interested in using is a transformer. We're going to patchify the EEG data and pass it through some transformer attention layers and convolution layers to learn an embedding. So historically, this field has mainly been with the use of CNNs or LSTMs, but we're seeing some really great improvements from using transformer encoders. So EEG image decode got some pretty good results on EEG2, which was basically the current state-of-the-art largest EEG image dataset. And the top row is the stimulus image, and the bottom row is the reconstruction. We see that there's quite a few improvements that we can make on the architecture side. Mainly, we can guide the prompt tuning in a more efficient way for multiple subjects, or we can incorporate active learning to explore how we can show different stimuli to fasten the fine-tuning process. We can also see how we can make an autoencoder that maybe makes the encoder learn better, and we can also guide the structural fusion process with image-to-image or unclip. So those are very low fruits that we can explore. And in terms of our data set, it's built specifically for image reconstruction. So we have 300 stimulus and 300 breaks, so one trial is 600 milliseconds, and that allows us to capture the majority of the brain response compared to other data sets that are much shorter, and so there's a lot of pollution. We also show natural images, so there's less of a risk of it being a classification task than we see in other data sets that have like maybe 40 or 10 classes. So far we're pretty open, and we have a lot of active project volunteers, and so we're always looking for more. We're collaborating with the University of Toronto to collect data with the Visual Reconstruction Lab. And we collaborated with Motive to have our own headset so that we can gather much more data quickly. And in the future, we're exploring some art exhibitions as well. So here's our headset. It's a 32-channel saline device, and it's wireless. So having this allows us to gather data way more than if we had to travel down to a lab. So this is what we'll use for our next data set. So yeah, image reconstruction is a subset of brain decoding, and this whole field is really exciting because we're finally able to kind of understand more complicated sentiment from non-invasive neuro signals. And so this has a lot of potential in clinical applications, such as helping patients communicate again, or in therapy in terms of identifying our own responses or mental visual imagery. We also think that this could be really helpful for contexts such as gaming, or in the far future, or like some more reachable communication with maybe other species. That would be really cool. But generally, we think it's pretty exciting to work on this topic right now because we're seeing the emergence of a lot of really powerful models and architectures, and combining that with new data sets would give us really good results. So we're focusing on EEG in particular because it seems like the most practical modality for everyday usage. It's mobile, it's fast, and it's the only affordable option for the everyday person. So anyways, that's kind of where we're at right now. We're working on gathering our next data set in a hackathon in May 1st. We do weekly paper readings. Everyone is welcome to join. And yeah, there's a lot of work that we want to do in building deep architectures, gather like a new stimulus paradigm, and also some infrastructure work on real-time pre-processing. So if any of this sounds interesting to you, or you want to kind of be a part of the group, you can join us on Discord. So anyways, that's all for us right now. I'm always happy to be collaborating, and thanks so much.
With that, let's thank our presenters again. Really great job and very fun projects. Very different. That's what you get by sampling the general public, what people are working on. Really fun.
Thanks.
Yeah, great job both.
Thanks for having me.
See you guys next time.
Bye.
Being as well. Bye.